morning, everyone. Good morning. Thanks. The one person who's been caffeinated this morning. Hi, thank you so much for being here this morning with me. I am really excited to share with you why I am excited about quantum computing, and in particular, Microsoft's programming language Qsharp and the Quantum Development Kit. So let's just get started. A little bit about me. I am a research engineer at an engineering consulting firm called Pensar Development, just a few blocks away from here in downtown Seattle. My background, though, is in experimental quantum optics. So I've spent a lot of time in dark labs looking for single photons, or maybe lots of them, trying to melt things with them. And in my spare time, I actually do a lot of writing. I'm really excited about trying to help communicate what is generally perceived as more technical or complicated science topics to a broader audience. So you can see I've got a bunch of free copies of all of these books here that you can come find me after the talk. Cool. So here's the audience participation part of the talk. I want to know, when I start with a new group, what you guys know about quantum computing, because I know I definitely didn't know very much when I started. So just shout some stuff out at me. What have you heard? It could be word association. It could be complete thoughts, but maybe not too long. Sorry? Non-binary. OK. Great security. Probabilistic. All right. Those are all pretty good ones. Anything else? Entanglement. There we go. That's a good one. Superposition. Cool. I think we've hit a lot of the buzzwords now. Awesome. So my phone knows that I am interested in quantum computing and likes to suggest articles to me a lot, which I assume is generally like one avenue how people learn about quantum computing. And when I read these headlines, and sometimes the articles inside, I wonder. So like some of my favorites here, quantum physics can explain much of the world's suffering. What came first, the chicken or the egg? Both, quantum physics says. The promise of quantum computing supremacy is bunk. Like, all of these titles, I feel like, would not communicate, even though I know something about the field, don't really communicate very much to me about what it is or what's even going on. And part of that is just because physicists are very whimsy and like to name things with very fun names like time crystals or quantum mana or magic states, and then we end up with pretty much everybody confused. So what in the heck is a quantum computer then? Cool. So yeah, this is a picture of some of the hardware, supporting hardware for what Microsoft's working on. But yeah, like given all of that, what are we actually even talking about? So we're all pretty familiar with what a regular computer is. You've probably got your phones in your pocket or your hands. That's a computer you can hold. You've got your car, your computer you can drive in. But basically, they're devices for manipulating information in the form of binary bits. And to change what those binary bits say, we write programs, which probably most of us here do. So really, quantum computing isn't that much different. Like, we still have a device that is storing information. We are still writing programs to manipulate what that device knows about, or what that information in the device is. But really, all we're swapping out is how we're storing that information. Now, instead of binary bits, your ones and zeros, now we're going to be using quantum systems. I'm going to leave that nebulous for a little bit because we're going to do some demos in Qsharp to kind of explore what that actually is. So if I were to try and kind of diagram like what a quantum computing system would look like, here you go. So you would definitely need your regular classical computer dev machine. So your desktop, your cluster, whatever you like, a classical computing resource, which is where you're going to be writing those programs to instruct the quantum systems what to do. That program is going to compile instructions and pass those along to a whole litany of other classical controls, other classical computers, FPGAs, things that basically translate those programmatic instructions, kind of the high-level algorithmic instructions, to like actual analog electronic pulses, and send those along to your quantum systems. Now, the quantum systems have to live in a very cold environment, and I'm not talking just your regular kitchen fridge or your chest freezer in your garage. They have to live in cryogenic fridges that exist at about a couple millikelvin, maybe more, but basically very, very close to absolute zero. For a reference point, deep space is about 4 Kelvin, so that's way too warm for quantum computing. So really cold. And what we can kind of observe from this is that this isn't exactly something that, even from a hardware standpoint, is going to be in your house anytime soon. This is kind of going to be similar to a lot of the models for early computing, where you had like a company or a university, that maintained the device, and then you could remote in for time on the computing resource. Now it would be via the cloud, but then dial up and whatnot. So you can kind of, a good way to like a mental model to think about where quantum computing fits in with the rest of our computing infrastructure is as a hardware accelerator. So kind of like GPU clusters that you can access in the cloud or in Azure, or specialized machine learning hardware, quantum computers are good at providing speedups for particular types of problems. That you're not going to be checking your email on a GPU cluster, and similarly, you're not going to be replacing a lot of those tasks that your classical computer is perfectly good at. So quantum computers will kind of fit in that same model of a specialized hardware accelerator. So given that, what would we actually speed up with a quantum computer? It's a good question. So there are lots of different kind of domains in which people are exploring what we can actually do with quantum computing. Some of these actually came up when we were shouting out stuff earlier, cryptography, both in the manner of breaking current classical protocols, as well as enhancing with the quantum technology to build new cryptographic hardware, accelerating particular machine learning protocols, and what a lot of the other folks here at Build from the Qsharp team have been talking about, the chemistry and material science simulation. So it turns out that a lot of the kind of chemical reactions and things that we have a hard time simulating and understanding now actually get a lot easier if you can just use a quantum system to simulate a quantum system. So, it kind of makes sense. But that's actually a really exciting application, because it can potentially have impacts to like understanding photosynthesis, helping us make fertilizer more efficiently, which right now consumes around 1% to 3% of the entire global energy budget. So there's some significant impacts. And so that kind of leads to the next obvious question: when is this going to be, like, when will we be able to do this? What is the time frame? The best way to understand that is to just take your application and start building it. We need to answer questions like, how many qubits do you need to do? Like, how many qubits do you need? What sorts of algorithms do you need to? Those kind of are interlinked. And you can see this is a picture from an experiment I was doing in the lab. I was definitely spending my time appropriately while waiting for data to come in. But more importantly, with these applications, who is actually going to develop it? Who would you guys guess could write a quantum program or a quantum algorithm? You can just shout them out. Nobody then? No one can do this? No, not me. Any guesses? Scientists? Okay, yeah. So it seems like you might need to understand a lot of different things to be able to write these applications. So who actually can do this? I would posit that teachers can do this, data scientists can do this, project managers can do this. Pretty much you can do this, and everyone can actually program for a quantum computer. This is my kind of primary thesis, and hopefully I can convince you that this is something that is a thing that you can just sit down and do yourself, maybe later, or maybe when you get back home. So given that, how are we going to do this? How can we learn together how to develop for a quantum computer? Some obvious challenges that might come along with this. Kind of as we saw with those headlines, I feel like a lot of the educational material you might find about quantum computing falls into one of two categories. It's those sorts of headlines and pop-sci articles, or graduate level research papers. So, between the two, if you want to actually understand what's going on, but you don't want to have like a PhD in math and physics and whatnot to actually understand the notation and syntax of what they're doing, it's kind of hard to find what the right material to learn is. It's also has been kind of hard to get hands-on. We don't have a lot of quantum hardware. There are a number of companies that have kind of a number of qubits you can work with, but there's nothing that really constitutes a full computer. And similarly, as I kind of alluded to, if you wanted to understand everything from like what's the quantum physics that's going on in your quantum systems, to like the FPGA programming for the signals that you're generating, to the cloud communication, if you wanted to understand that full entire stack, that would be a lot. I certainly don't understand that entire stack. Similarly, when I push the power button, I don't know how my computer turns on. Like, I have some general ideas, but that is a huge and incredibly complicated stack of protocols, procedures, but it works pretty well. So thankfully, my slides came up today. So yeah, what I'm trying to get at, though, is we don't have to necessarily understand every detail of every layer to be able to program for the quantum computers. So we have our classical computers right here, right now. So let's actually, what can we do with those to understand what we might be able to do with a quantum computer? So meet Qsharp and the Quantum Development Kit. Qsharp is a domain-specific programming language specifically for expressing quantum algorithms. Now, it kind of makes sense that we'd want a new programming language for this because our quantum systems operate differently, and in fact, by different laws of physics than our classical bits. So it kind of makes sense we might want a different language to actually describe what's going on there. And other really cool things that I'm excited about, it was actually announced by Martin on Monday, but the libraries were already open source, but the rest of the compiler and the Quantum Development Kit will be open source by summer. And there's a good blog post on the Microsoft Quantum blog about that. But you can see I've got a screenshot over here of a simple Qsharp program running in VS Code. So Qsharp is built off of .NET Core, which is really cool because it means it's cross-platform. You can use it pretty much anywhere you like. It also has great extensions for Visual Studio and Visual Studio Code, which means I'm mainly a Visual Studio Code user, but you have the full IntelliSense. You can get hinting, a lot of the stuff that you're kind of used to with a lot of other languages in your development environments. You have for Qsharp. So if we're to look at what's actually going on here, so I said it's built off of .NET Core. What happens when you write a Qsharp program is you're writing some operations and functions yourself, and the Quantum Development Kit has a bunch of libraries that you can pull from already. So algorithms that are already implemented that you can use, helpful utility functions, all kinds of stuff. So between you compile all of these together, and your Qsharp program gets executed by a host program, which in this case is a C# program. And what you write in your Qsharp code doesn't know anything about what it actually will be running on. And the host program is in charge of sending your program to the appropriate target machine. So you can target your program to a simulator, which is great because that means you can run you can simulate your program on your laptop. You can do usually around about 30 on a reasonable dev machine, and possibly a few more on if you use cloud resources. But that's a great way to get started because you can just start playing around with stuff. Another target machine you can use that's provided with the Quantum Development Kit is the resource estimator. So 32 qubits, or around 30 qubits is not so many. There definitely are applications we can think of where we might want more. But the question is, all right, I've written this Qsharp program. What do I actually need to run it? That was kind of one of the questions that motivated us for trying to understand what's going on. And the resource estimator will actually tell us how many qubits we'd need to run it, what type of gates we would need, which gives us a really good way to say, all right, I have this application I'd like to use. Do I need 5,000 qubits? Do I need 50,000 qubits? Do I need 5 million qubits? And that can help us understand, the timelines, or if maybe we should try to do some optimizations on our algorithm. Cool. So what really got me excited about Qsharp, as you saw in the lab, I do a lot of stuff in Jupyter or with Python and in Jupyter notebooks, and Qsharp is actually interoperable with Python. And I think this is really important because I think the Python community is a really kind of great place. It's very open and welcoming, and so we can now basically open up Qsharp to that entire community, as well as to help kind of onboard people. And as a much more recent addition in the, I think it was 0.5, Jupyter, there's now a Jupyter notebook kernel for Qsharp, which means you don't have to handle any of the back end. So basically the host program, target machines, like normally you would you'd edit a C# driver file to do all of that. But if you use the iQsharp kernel, that's basically all abstracted away for you, and you can just run your functions and operations in Qsharp, just kind of like you would any other language that you can run with the Jupyter notebooks. And I think this is just one of the coolest things because I basically learned to program with Jupyter notebooks. I came from Mathematica. I was actually a kernel dev at Mathematica for a while, so this whole environment of being able to kind of like play around and evaluate parts of your code, come back to it, put documentation in line with it, is a really powerful teaching tool. So let's dive in. I'm going to switch over to the demo here. Cool. So I'm going to launch Jupyter Notebook here. And so I'm launching Jupyter Notebook right now with a Python kernel. And we're going to be using Python to interoperate with Qsharp and actually interact with things. So it will probably take it a minute to spin up here. Cool. And for the record, all the code and everything you see here, there's a GitHub repo that I will be sharing the link on Twitter, and y'all can find it on GitHub there. F11, cool. Awesome. Okay, so let's start by doing kind of the standard Pythonic thing of let's actually just import the package that we want to use, which in this case it's called Qsharp. And it will take it a moment to spin up all the .NET stuff. Also, if you like how the Jupyter Notebook goes to slides, this is a really cool Jupyter plugin called Rise that I found a couple days ago, so I'm super stoked about it. Cool. So I had it also just print out the versions here so I could make sure I was on the right version. So let's return to the what I was saying before about the quantum systems being our method of storing information. Before, with our classical bits, it's ones and zeros, right? So for our quantum bits, or qubits, is basically probably the thing you've either heard about or will now hear about. Qubit is just quantum and bit smushed together. And so a qubit is represented by a vector of complex numbers. So in particular, for a single qubit, you have a 2-entry vector. for 2 qubits, you have 4 entries, so it scales 2 to the 2n, yeah, or minus 1, I forget. No, 2 to 2n, 2 to the n. Right, and you can kind of see there's this weird symbol here to the left of it. This notation is called a ket, so you would pronounce this ket x, and it's basically another way in which physics kind of came up with a cute naming thing. So if this is a ket, if you flip it the other way and you have an angle bracket and then a pipe, that's a bra, and so you put them together, they make bracket. So, but the main point is the kets here is basically going to be the notation that we use to just simply label a vector. So it's the same thing, don't worry about it. What can we actually do with a qubit? You know, I've gotten us all excited about programming quantum computers, so what are we actually going to do with the resources? Well, firstly, you can prepare a qubit. You can do operations with a qubit, and you can measure a qubit. And of all of these, kind of the most interesting one is, compared to our classical bits, is the measurement. So we have this quantum system. It's represented by a vector of complex numbers. When we measure it, we don't just get that vector of complex numbers out. We get a 1 or a 0. We're classical beings. We cannot see. We're not Paul Rudd and Ant-Man. We cannot see into the quantum realm. So when we make measurements, we get classical data back out. And so part of the art of quantum algorithm development is trying to arrange and get your end quantum, or your end like data stored in your quantum computer in such a way that when you make the measurement, that one bit communicates what you want to know about it. So we're going to look at some examples of this. So let's start by preparing a qubit. So you can see what I'm doing here from the Qsharp package. We're going to use compile. So we have a couple different ways to actually use Qsharp in Python. This is a good example of one of them. I can pass here directly just the string. You can see it's a multi-line string of the code that I would have maybe in your standard Qsharp file. So I can run this. It's going to actually compile this for me. And what's cool is prepare qubit now is actually like a Pythonic object. So if I go to look at attributes and I hit tab, I can see my options are estimate resources, simulate, and source. But what I'm interested here in is simulating it. So what's actually going to happen? Let's look at the code. So our operation here is called prepare qubit. Qsharp is a typed language, strongly typed. So we have no inputs here, but we can see the output type is unit. Then we have this using statement, which basically tells whatever our target machine is, whether it's the simulator or hardware, hey, heads up, I'd like a qubit, please. So I want 1 qubit. We're going to call it qubit. And I'm not actually doing anything with the qubit here. This is just allocating the qubit. And then dump machine here is a kind of a utility function that allows us to see what the simulator is actually storing about the qubit. Now, dump machine is not something you should use in production or in any actual quantum algorithms. I'm doing this here to basically show us what the simulator is recording so that we can kind of talk about it and explain it. But in general, you wouldn't be able, I can do this because I'm using the simulator target machine, but if I were using a real hardware, I wouldn't be able to do this. So you don't want to write your program to rely on this so that when you actually go to run it on hardware, it won't work. So let's see what happens. So we get this output here from dump machine. We can see the parens here, which is just the unit return. But it actually prints out here what it's storing for our qubit. And if we look here, I've just copied and pasted it up here. This is pretty close to what we saw earlier as representing our qubit. So the only difference here is that you can see there's another column that represents the coefficients for the imaginary parts of each entry. So this 1 corresponds to the first entry, 0 to here, but these are the real components, and these are the imaginary components. So that's kind of why I continued to write out 0 times I, even though obviously it doesn't matter, it's still 0. Cool. So now let's actually use this and do something fun. Generate random numbers. This is definitely a thing we can already do with a lot of the qubits that we have in hardware, and is pretty important from a cryptographic standpoint. A lot of times, our entire cryptographic chain of trust, I have not had enough coffee yet, relies on where your source of randomness is coming for your key. And so if that's compromised, everything else down the chain is compromised as well. So if you can replace procedures, like the stuff built onto your CPU with a quantum system deciding what your random number is, you can actually write a proof of security that is not computational. You can write it basically from the laws of physics. This is random. So that, security people like that. So let's give this a go. What I'm doing here, I'm going to demonstrate the other mode of using Qsharp and Python, which is loading it from other files in your directory. So this is just a snippet I had it up here at the beginning, but I've got a couple files in my repo here. One is, these are Qsharp files, you can see up here. And I've defined a namespace, and then our imports, and then the functions and operations. And in Python, what that means with the Qsharp package, we can just say, hey, from this namespace, let's import one of the functions or operations. So that's part of what happens when Qsharp starts up. It looks through your directory, finds things that are also in your project. Cool. So now it knows about the operation QRNG. So let's take a quick look at what's actually going to happen here. So this part probably looks a little familiar. We have the same sort of using, hey, I'd like a qubit, please. And then we're going to do this operation, the H operation. We'll talk a little bit more about this in a minute. The H stands for Hadamard, but it's a very, very useful quantum operation that doesn't really have a good analog to our classical Boolean logic gates. But it kind of is as useful as like a not or an and or something like that. So we do our operation, and then we do a measurement. And what we're doing here, so we're going to return this, and you can see our return type here is result. So we're going to return the result of measuring our qubit along the z-axis. Now, it doesn't matter too much. What that means is kind of like I was talking about before. We can't just measure that entire vector. That z basically tells us, what subset of that vector we want to look at, or what component we want to look at. And we reset the qubit because as a part of the promise we make to our target machine when we say, hey, can you give me a qubit, is that we will return it back to the simulator clean, re-prepared back to that 0 state, or the 1, 0 qubit that we were looking at before. So kind of like good stewards, we return it back the way it came to us. Cool. So another cool thing is that when we write documentation in our Qsharp files, that actually kind of comes along to the Python side as well. So if I ask the Python kernel, hey, what does QRNG do? I can actually see the doc strings that I wrote in the Qsharp file. And actually, if you were doing this in Visual Studio Code or Visual Studio, this would also get pulled along in IntelliSense as well. So I find that very helpful so that I don't have to tab back and forth between things. So that, let's actually look at it real quick. It says that given a qubit initially in the 0 state, if we apply that H operation, and it gives us this particular state. And more importantly, it returns a 1 result with a probability of 0.5 and a 0 result with a probability of 0.5. So this is going to be what we expect here to happen. Is basically this is a really good coin flip that is, if we were running this on real hardware, guaranteed by the laws of physics to be truly random. Since we are technically running this on a computer, a classical computer simulator, this still technically is pseudo-random. So let's just actually give this a go. So I can use list comprehensions just like I would regularly in Python and say, I would like to do this 10 times and get 10 random numbers. And you can see it works. Yeah, the numbers do change. Just checking. Yeah, so that isn't super exciting. There's obviously a ton of other ways we could get random numbers. But it is cool because we now have the opportunity, we've written this code, and we could actually run it on real hardware. So let's talk a little bit more about what that H operation is. So I'm going to pass this time the option of, I basically gave myself a toggle for the print statements. So I will set the simulate to verbose mode this time and see what we can find out about what's going on to our actual quantum state. So you can see, just like before, when we get a qubit from the simulator, it starts as a 0 in the 0 state. So that means it's 1 in the first entry and 0 in the second, and no imaginary components. And so I also added a dump machine after we did the H operation. And you can see what happens. So now we don't just have a 1, 0. Now we have, okay, this is 1 over the square root of 2. But we have, more importantly, the same number for both 1 and 0. And that's basically what means when we actually sample this as a probability. We will measure 0 with 50% probability and 1 with 50% probability. And you can see that one time that we ran that, we got a 0. Cool. So this is great. We now we've prepared a single qubit, we've done an operation with it, and we've measured it, gotten 1s and 0s out. Cool. But generally speaking, we're going to need more than 1 qubit to do something interesting. So let's talk about 2 qubits. So I think somebody at the beginning shouted out entanglement as one of the things that they'd heard about quantum computing. This is a really great way we can actually explore what entanglement actually is. So I'm going to do the same thing as before. I have in that file in the directory a namespace, or from the same namespace, an operation called entangled qubits. And I will turn on verbose is on. So now we have 2 qubits. And you can see our dump machine actually now has like 4 entries. So that's the 2 to the 2. And how we can understand like what these map to. Before, the first one just meant that's the 0 state for the qubit and the 1 state, just labels basically. Now the labels for 2 qubits are going to be kind of the same way you would count binary bits. So this would be, the first entry here would be information about both qubits being in the 0, 0 state, then 0, 1, 1, 0, 1, 1. So we can see here when we first get 2 qubits from the simulator, they are 100% both in the 0 state. So that makes sense. That was the promise made to us by the simulator. And after we do the entanglement operation, which is actually 2 gates, or 2 operations, but we end up with this state. So what do we see here? We now see numbers only for the 0, 0 entry and the 1, 1 entry. And so what that means is that when we measure these 2 qubits, we will only, if we measure one of them as a 0, we know there is no chance that the other one will be something different than what we measured the first time. So basically our only possible measurement outcomes are 0, 0, and 1, 1. And again, from the same argument of these being the same number, it will happen with about 50-50 probability. So let me try running this a bunch of times again. And you can see each time we measure the pair after entangling them, we do in fact get either 1, 1 or 0, 0. So thankfully, the laws of physics work out. Cool. So I think that's most of what I've got for this part of the demo. Actually, are you guys keen on seeing some more demo stuff? Yeah? OK, cool. I've been going faster than I thought. So let's talk about an actual quantum algorithm. So just as an initial disclaimer, this is definitely a toy algorithm. The objective that you're trying to solve seems a little contrived, and yeah, it is. But what is useful about it is that you can generalize it, and you can use it kind of as a subroutine for a larger algorithm and still get the speedups from. So let's set this up. Let's say I had a function that has a 1-bit input. So this is just classical function, 1-bit input and 1-bit output. How many different options would I have for that function? I kind of drew a little picture here to represent that. So if my options for input are 0 and 1, and my options for output are also 0 and 1, there's basically 4 different ways I could map the inputs to the outputs. So if I just basically said, all right, I'll output what you gave me, I'll just call it the identity function. If I swap them, that's a not. If I send both inputs to 0, call it 0, and same for 1. So with that as a setup, let's talk about Deutsch-Jozsa. So this is the toy algorithm that I was mentioning before. The problem statement for it is, if I'm given a black box implemented on my quantum computer that actually computes this classical function f, one of those 4 options, basically. So it takes 1 bit as input and outputs 1 classical bit. I would like to know not what function is in that box, but a property about that function, and in particular, whether it is constant or balanced. And I want to do this with as few kind of tries of throwing data into the box. So given that this is just 1-bit input, technically there's only 2 possible inputs I could give to it. So from our human perspective, that doesn't seem like a huge speed up, but this actually does scale for n-sized inputs and n-sized outputs. So I just don't like drawing that many lines, connecting the dots. And Deutsch-Jozsa can actually do this in 1 query. So we go from 1 query with the quantum computer to two queries classically. But like I said, it always is just 1 query, no matter the size of the input. So this global property, balanced or constant, is pretty straightforward. Basically, the identity and not versions for this function f are the balanced category because, well, you kind of like map, you cover all of the same outputs as inputs. Here, these are constant because, well, they constantly output the same thing. It's not too complicated. And so my goal here is to, with basically 1 query to this box, figure out which category it's in but I don't care what actually function it is. That's not important to me. Cool. So let's, I again have, so I'm going to use the compile option here again. So I'm just passing stuff in, and I'm even passing stuff in here and using stuff from the Qsharp file that's also in my directory because it was too big to put on the slide. So I've got an operation here that's going to ask, is our 0 oracle? So oracle here is basically the name that I've given to this black box that I don't know what's inside. I know that there's a function in it, but I don't know which one. And so here I'm just asking, I know ahead of time that I have the 0 oracle, and I'm trying to ask, is it balanced? And so if it's the 0 oracle, we would expect that this should be false, because the 0 oracle would map everything to 0, which is a constant, not a balanced. So let's compile that. And thankfully, my mental math here worked out. So yeah, that's what we expected. That's not, we saw from our picture, actually I did have it repeated here. The 0 oracle here is constant, not balanced. We can do this again for the not oracle, which should be balanced, so this should be true. Cool. And let's put this all together, and I have a operation in my Qsharp namespace as well called run the entire algorithm, and I will actually check that all of the oracles that we implemented here actually do indeed, with one query, tell me whether they are constant or balanced correctly, which I realize just having a printout that says all tests pass is maybe not so convincing, but the fun part is you can check out this repo yourself and actually look at what's going on and try it out. Here I had it at least say what it found. So the 0 and 1 oracles we would expect to be constant. So are they balanced? No. And the ID and not oracle should be balanced because they cover all the outputs. So cool. Alrighty. One other thing we can note from this is you can see that the output, there are some interesting general guidelines for writing quantum algorithms that allow us to kind of get around that whole measurement challenge of not being able to read out our full final state. So one of the things that you can kind of see from this example is that we like it when our quantum algorithm basically has a yes or no question at the end. That makes it really easy to kind of design our quantum state so that we basically have one entry we're looking at in the vector, and we want to know whether, and we can try to use the quantum properties of the system to create a really high probability that, or certainty in some cases, that we actually get the answer we want, which, since we're measuring a 1 or a 0, I mean, that's a yes or no question. So basically, you know that your problem might be a good candidate for a quantum computer if you can kind of like boil it down to a yes or no question about whatever your input is. Cool. So let's hop back to the slides. See how seamlessly I can do this. Cool. So we've seen now playing around with Qsharp in Jupyter Notebook and with Python. I was doing this in Jupyter Notebook here, but of course you could write your own Python scripts in files or use IPython. Like any of the ways that you like using Python or .NET if you want to just write Qsharp directly, there's lots of options. And so you can really use what you're most familiar with and what you like. So we have all of this promise and all of these applications, but how do we actually get there? Well, Qsharp is a really awesome start to help us understand and actually start writing some of those applications, but we need to write that software. And we've seen from experience that communities of people write software. Watching and kind of understanding how the open source communities for tons of different languages, including a lot of Microsoft stuff now, it's really neat to see how people work together to make these really awesome, cool software projects. You know, everyone from data scientists, Python developers, academics. But what we know right now is that a lot of those people are not engaged in the quantum computing community. And I would challenge that we actually do want everybody involved here, because that's how we're actually going to get the ideas to figure out where we can apply it next. Like, you know, if the same 3 people are just thinking about this in the room somewhere, they're not going to have new ideas or different ideas. Like, I love working on the interdisciplinary team that I work with because I work with mechanical engineers and electrical engineers, software engineers, some that do FPGA design, and we all have different things we bring to the table. So it's really important that we include everyone when we're trying to develop these applications for quantum computing. So how do we're kind of at a crossroads now. Quantum programming is really starting to be a thing. We have now a language we can work with. We have a number of different platforms we can use. So how do we be intentional about this and create these developer communities the way we want to see them? There's lots of cool things that at least I've noticed from other open source communities. Things like encouraging and supporting member contributions. I love it when I come upon a project that has like a good first issue tag, because I know like my first public PR was last year build. So I had not, I'd been kind of too scared or intimidated by contributing to these projects. So having maintainers and other community members be like, hey, this is a good one. This is pretty easy. It's not going to be high. It's going to be a good project for a newcomer to our repo. Other things that are really important about creating our new quantum programming community are having codes of conduct, which create safe spaces for our members to actually be. Another is good documentation tutorials. I know, as I'm an experimentalist, I like to code experimentally as well, which means I will probably not read the docs first. Shame on me. I will just get a sample from a tutorial that I find somewhere, try to build it, try to use it, tweak it, and then probably go read the docs when it doesn't work. So having those tutorials, having kind of, even if it's just a really simple walkthrough of like how to use a qubit and do a QRNG like this, or do just get your environment set up for Qsharp. Things like that are really helpful, and I think can help people who are maybe too intimidated by looking at docs or looking at a full repo, samples in the repo, which there are lots of good samples in the Qsharp repo, I should say. And lastly, meetup groups and hack nights. I really love, I live here in Seattle, so obviously there's lots of really great tech people here in the area, so I go to PyLadies Seattle all the time. But it's really great to find other people who are excited about the things you're excited about and like compare notes in a more synchronous fashion than just Slack messages or otherwise asynchronous stuff. So let's really be intentional and use these lessons that we've learned from other open source communities, other programming and development communities in general, and make the quantum programming community really cool and a great place to be. So, given that, what can I do? Math joke. So, because I is square root of -1. Now that I've explained it, it has totally lost all of its humor. So, obviously a good first step is to just go try Qsharp for yourself. Go to there's lots of different options. I'll show some links on the next page, but if you want, you can even just try it in your browser, going to using a Jupyter Notebook and using the Qsharp kernel, so you don't have to set up anything on your machine to actually go try this. Start a meetup. I do lunch and learns at work a lot. When I find something interesting that I'm learning about, I just tell my team, hey, come have lunch with me, we'll talk about this thing. That's something that's fun to do. Write some of those blog posts and tutorials, and hopefully we can kind of provide feedback on those as a community. And more importantly, leave the community better than you found it. So, finding and contributing to the official docs, to fixing bugs, and just in general acting intentionally to include as many people as possible in this quantum programming community. So I mentioned some links. So a good first starting place is actually a new group that myself and Ralph are starting up. The URL is just qsharp.community. So it's a Qsharp, or it's a GitHub org where we're going to try and collect a bunch of different projects, examples, tutorials, things that that we can help maintain as a community and help inspire people for their own projects and find what they might want to work on. As always, read the docs, docs.microsoft.com/quantum. The shameless self-promotion is Chris Grenade and myself have been working on a textbook. That's basically, this talk is kind of a short preview for. So I've got a bunch of free codes for those that just come up and talk to me after the talk. I'll give them out. And obviously, I've also found a lot of good information on Q&A sites. So Stack Exchange, Stack Overflow are great. Reddit, user beware. But in general, I will end with this and then take questions. But go make the quantum development community the best community it can be. Thanks. Cool. Is there any questions? Yeah, and please use the mics so that they can be transcribed.
So super quick question. The hardware that you guys are using, is that D-Wave by chance, or what is that in-house hardware for the quantum processing?
Oh, that picture that I had?
Yeah.
That was actually Microsoft, from Microsoft, some of their hardware that they're using
nice.
in those fridges.
Okay.
So the short description of what it is when you put your quantum systems in a fridge, you basically have to set up a bunch of different thermal stages to cool the things down, because you can't just, if you have regular electrical wires that are connected to your computer, those are at room temperature, and anything that conducts electricity also conducts heat. So you have to have these kind of like floating islands that basically step down your temperature, and then you have different, so basically that's what that is, and it just hangs, usually suspended in like liquid, sometimes it's liquid helium, sometimes they're dry, but yeah, that's the idea, is that's kind of like a pyramid of temperature down to the very lowest one, which is where your actual chip sits.
So was that like a partnership then with D-Wave, or was that literally like totally separate? Like that wasn't.
That's Microsoft's own hardware.
Well, that's really neat.
Endeavors.
Awesome.
Yeah.
Cool. Thanks.
So the fundamental building block of a CPU is a transistor. What is the fundamental building block of a quantum chip?
A qubit. So qubits are your information storage, and then depending on, there's tons of different ways you can make quantum systems, right? Like what I've normally worked with is photons, which are great as individual qubits and for doing cryptographic things. But for a computer, you need them to interact, and unfortunately, photons don't like to work together. So in hardware systems like the type that Microsoft is working on, and other groups with superconductors, you're using microwave pulses from external fields to basically kind of get them to interact and produce the operation that you want on one or more qubits. So that's where that classical control kind of intermediary going from your actual desktop to the quantum systems, that's doing a lot of translation to figure out, okay, I'm going to make these arbitrary waveforms, which generates the magnetic field in this position that actually manipulates the quantum system.
So as I understand it, there are quantum logic gates. What are those logic gates? Like, how are they made, essentially, I guess?
Well, so you make them by usually electromagnetic pulses. So they're kind of transient. They don't exist as a physical thing. But more generally, there is kind of a similar, so we know from classical computing, like if you have a NAND, is it NAND and maybe one other thing, you can make you can combine those to make any sort of arbitrary logic. There are similarly minimal gate sets for quantum computing that give you the ability to make basically arbitrary operations. That's not something I'm an extensive expert on, but I do know that basically there's lots of research on like a number of different kind of core gate sets that would give you arbitrary operations. And it's like usually, I think, about 3, but don't quote me on that. So it's not like you need 40 gates. There's like a handful.
Hi. I'm not by any means knowledgeable in this area, but the little thing I read told me that what the quantum program is giving it's a probability. and in the end, you find the probability of your answer. So you can have multiple stages, and you get the, let's say, make the best decision. Here it was only 0 and 1. Can you explain what's going on?
Sure, sure. Yeah, so you are entirely correct. The entries in that vector basically do describe effectively a probability distribution, that when we do that measurement, we're sampling that probability distribution. Now, I like to make those distributions certainties, so it's easier to talk about what's going on. But like we saw when we did that H operation, that gave us like the 0.7 and 0.7. If you square those actually turn into half and half. And so that's your probability. It's a uniform probability distribution over 0 and 1. And so there are definitely, you can do probabilistic quantum algorithms, which basically you're trying to get the answer you want to get to have the highest probability, but you can also actually make deterministic quantum algorithms. So Deutsch-Jozsa is actually a deterministic algorithm that does have a 1 in a particular place in that vector, so when you measure it, you know that that's your answer. So yeah.
Okay.
Cool.
Can you explain us about the topological qubit? I read about it, but it didn't come up over here.
I think the short answer is I cannot. I mainly did photonic qubits, but I do know if you go check out the quantum booth, Microsoft has some quantum booths out in I think it's the App Center, so if you go where the big glowy edge thing is and to the right, go ask a bunch of folks there. They will know a lot more about that than I do. Hi.
So I've heard a fair bit about quantum computing, but I'm having a bit of trouble figuring out the application for it. Everything I've heard so far seems to depend heavily on random number generating. Is there an application for it, a real-world one right now, that isn't based off simulation? Or is it mostly simulation-based?
I think I understand. So if I understand the question correctly, you're asking where, like, what near-term applications look like for this?
Yeah, so what would you actually use it for?
Sure. Other than just having fun at 2 a.m. on my computer when I'm waiting for other things to compile. Good question. So kind of one of the things I mentioned before about applications, there's definitely like long moonshot sort of things, which I think are generally speaking more like the Shor's algorithm, like factoring RSA. Like that will take a significant number more qubits than we currently have, orders of magnitude. So, but what is exciting about kind of what we see in the near term with the types of real hardware resources we have, as well as the simulation, is simulating other quantum systems. So like there's lots of cool, Microsoft has a partnership with Pacific Northwest National Labs, which does a lot of quantum chemistry stuff. And so they've released some like quantum chemistry libraries that actually go with Qsharp, and you can actually simulate electronic levels of different atoms and molecules and things like that. So I really think like some of this material science stuff, just basically helping us understand quantum mechanics and other like chemistry better is definitely where a lot of the initial stuff is going to be interesting. And the other thing that we've learned a lot from just playing around with simulators and stuff like that is the quantum-inspired algorithms. So Martin from the Microsoft Quantum team, and as well as the 2 startups that spoke with him, are doing quantum-inspired algorithms. So basically from trying to understand how quantum algorithms work and write those, because it is a very different sort of way of thinking. You don't have, ones and zeros. You can't make copies of things. Like there's lots of weird rules there. But if you kind of use those as inspiration, they've actually found ways to speed up classical algorithms that, with classical techniques, there's no quantum necessarily to it, but using lessons that we've learned from ways you might manipulate data, quantum systems. So that's another thing that's kind of been really exciting as of late, coming from even stuff with simulators. But yeah, is that cool? Any other questions? Okay, if you could go to the mic.
So you have spoken about that there are these certain specific applications like machine learning, cryptography, where certain quantum computing might be a good area to use. But what do you think that maybe speaking in terms of long term, that can we like move towards quantum computing for a regular like laptops and desktops? Or is that not what quantum computing is for, and only for these needs? These specific applications is what quantum computing is required.
Okay. I'm sorry, I'm having a hard time with the acoustics in here, but I can speak a little bit to the quantum machine learning applications. A lot of what we've seen with that is we know that there's particular kind of subcomponents or subroutines of quantum machine learning protocols that we do know how to speed up, and in fact, sometimes exponentially. One good example of this is an algorithm called HHL, which does linear regression exponentially faster. But kind of the challenge with this is we can do that, but we have to translate our actual classical data into and transcode it into the qubits. And so far, we don't really have any good ways to do that, wherein the overhead from doing that does not blow away all of the advantages you get from running it on the quantum systems to start with. So that I don't think rules it out as a possibility for application. I think it means we have to kind of be more clever about how much data we need to actually pass to it, in what ways, and things like that. But yeah. Cool. I think we're at time. But thank you so much, everyone, for joining me. And if you have any other further questions, come up and talk to me. Go check out the Microsoft booth out on the floor. And yeah, have a great day.